Welcome to the Deep Dive. Today we're diving into one of the cosmos's biggest enigmas, dark matter.
Right. This stuff makes up about, 27% of the universe's energy?
Exactly. And it basically acts as this invisible framework that galaxies, well, hang upon.
But the real puzzle is, we can only sense its gravity. We can't see it, can't touch it.
It's like a cosmic ghost shaping everything, yeah. Super weird.
Absolutely. And that sheer mystery, it's really spurred some incredibly creative science.
Like what we're talking about today.
Precisely. We're focusing on a really ingenious approach, actually. Hunting for a specific dark matter candidate, the ultralight dark photon.
Ultralight dark photon. Okay, that definitely has a sci-fi ring to it. What's the deal with this particle? Why is it interesting?
Well, it's not just, a wild guess. The idea actually pops up in some string-inspired theories.
Ah, okay. So grounded in some heavy-duty physics trying to unify everything.
Exactly. And the thing is, if these particles do exist, they might have unique effects on the universe, maybe leave some kind of detectable signature.
Right, something we could actually find. Now, people have been looking for dark matter for ages. What are the usual ways they hunt for these dark photons?
Well, the traditional methods involve building really sensitive detectors deep underground, shielding them from other noise.
Lab-based stuff.
Lab-based, yeah. And also using powerful telescopes looking for astronomical signals. These are crucial, but they do have limitations.
Especially for certain types, like these super light ones.
Exactly. Which kind of brings us neatly to the main event for this deep dive.
Using NASA's Parker Solar Probe, the Sun Probe.
That's the one. Repurposing a spacecraft designed to study the sun as a dark matter hunter. It's a really clever scientific pivot.
Okay, I want to understand how that even works. So our mission today, explore this clever approach, see what they found or didn't find. And our source for this is physics.com.
Sounds good.
Right, let's start at the basics again. You said dark matter is like the universe's scaffolding. Can you paint that picture a bit more?
Sure. Basically, the gravity from all that dark matter is what pulled regular matter together after the Big Bang.
So without dark matter, no galaxies,
Right.
no stars clustered like we see them.
Probably not. At least not in the same way. The universe's expansion would likely have just pulled everything apart too quickly. Dark matter provided the extra gravitational oomph needed.
The invisible hand pulling the strings, gravitationally speaking.
That's a good way to put it. And what's still so baffling is that, apart from gravity, we just haven't seen it interact. Not with light, not with any other force we know.
A gravitational giant, but otherwise
Yeah.
a ghost. Okay, let's get into this ultralight dark photon. You said it might mediate interactions between other dark particles, like a photon does for us.
Exactly that analogy. So we have electrically charged particles interacting via photons, right? That's electromagnetism.
Yep.
The idea is maybe there's a whole dark sector with its own particles and potentially its own forces. The dark photon would be the carrier, the messenger particle for one of those hypothetical dark forces.
So it's like a counterpart to our photon, but operating in the dark realm.
That's the concept, yes. A fundamental particle, just hidden from our usual view.
Okay, got it. So how on earth do you go from studying the superhot sun to finding these hidden dark photons with a solar probe?
This is the really clever part. Scientists figured out that under the right conditions, these dark photons could actually transform into regular photons.
Change into light we can detect.
Precisely. And the area around the sun, the solar corona, it turns out that's a pretty special environment where this conversion could be, significantly boosted.
Boosted, like a natural amplifier out in space. How does that happen?
It comes down to an idea called kinetic mixing. It's a bit technical, but imagine the dark photon and the regular photon are like two very slightly connected systems.
Connected how?
Think of it like they can subtly influence each other. This tiny connection allows a dark photon to essentially oscillate or morph into an ordinary photon and vice versa.
Whoa, okay. Like it can swap identities?
In a way, yeah. It's actually a bit similar to how neutrinos can change between their different types, their flavors. This kind of mixing is predicted in quite a few theories that try to go beyond our current standard model of particle physics.
Mind-bending stuff. Okay, so the subtle connection lets them swap. Now, you said the solar corona, the sun's atmosphere, really helps this process. What's special about the corona?
The corona is this incredibly hot ionized gas, plasma. It's full of free-flying electrons.
Right, super hot plasma.
And these electrons interact with regular photons passing through. This interaction effectively gives the photons a kind of mass while they're in the plasma.
Wait, photons have mass in there. I thought they were massless.
They are fundamentally massless,
Ma-
but in the plasma, they behave as if they have mass because of these interactions. And crucially, this effective mass isn't constant. It changes depending on how dense the plasma is, which varies with distance from the sun.
Okay, so the density changes, meaning the photon's effective mass changes depending on where it is in the corona. Interesting. How does that help find dark photons?
This is where it gets really cool. It's called resonant interaction. Imagine the dark photon has a specific, tiny, but real mass.
Okay.
If that dark photon travels through a region of the corona where the effective mass of the regular photon exactly matches the dark photon's real mass,
A perfect match.
a perfect match, then bang, the conversion process gets a massive boost. It resonates, like pushing a swing at just the right moment to make it go higher and higher.
Ah, I see. The resonance dramatically increases the chance of a dark photon flipping into a regular photon.
Exactly. And when that happens, you'd expect to see a sudden burst of photons, all with pretty much the exact same energy, a nearly monochromatic signal.
Like a tiny laser beam signal.
Sort of, yeah. A spike of light at a very specific frequency, where the frequency tells you the mass of the original dark photon.
That sounds like something you could potentially spot, even against the sun's background noise. So why haven't we just pointed radio telescopes on Earth at the sun to look for this?
People have tried and still do. But ground-based radio telescopes have a couple of big problems for this specific search.
Like what?
First, our own Earth's ionosphere, the charged layer high up in the atmosphere, acts like a mirror for low-frequency radio waves. Anything below about 10 megahertz gets reflected back into space,
Okay, so it blocks the lowest frequencies.
which means it blocks signals from potentially very low-mass dark photons, those converting below that frequency limit. We're talking masses above about 10 to 6 electron volts, roughly. Anything lighter is hidden from the ground in radio waves.
Gotcha. What's the other problem?
Just distance. The sun is far away. Any faint signal produced in the corona gets incredibly diluted by the time it reaches Earth.
Right, the signal gets spread out and super weak.
Yep.
Okay, so the ionosphere acts like a filter, and distance kills the signal strength. How does Parker's solar probe beat that?
Well, its whole mission is to get closer to the sun than anything ever before, right?
Yeah.
It flies directly through the corona.
So it's right there where the action might be happening.
Exactly. That gives it two huge advantages. First, in situ detection. It's measuring right there, inside the plasma, before the signal gets weak or blocked.
Makes sense. Advantage 2.
Its radio instruments are designed to detect a really wide range of frequencies, crucially including those very low frequencies, down to 20 kilohertz that are blocked from Earth. So it opens up the window to potentially much lighter dark photons.
Okay, wider frequency range, including the low end. Anything else?
Yep, its orbit is highly elliptical. It swoops in close, then swings back out.
So it samples different distances.
Exactly, which means it travels through regions with different plasma densities and therefore different resonant frequencies. It can potentially probe for dark photons across a range of possible masses just by flying its normal mission path.
Wow, okay. That is seriously clever, using the probe's location, instruments, and orbit all together. So, the big question, did it work? Did Parker find those telltale energy spikes?
Well, the researchers crunched a lot of data from Parker's close passes. They also used data from another mission, Stereo, to cover even lower frequencies.
And
The verdict.
the verdict was they didn't see any statistically significant spectral bumps or distortions that would clearly signal dark photons converting.
So, no detection. That feels a bit like a letdown.
It might feel that way initially, but in science, a null result like this is actually really, really useful.
How so? Finding nothing tells us something.
Absolutely. By not finding a signal, they could say, okay, if dark photons with masses around 10 to 9 eVc exist, that's about a billionth of an electron's mass, super light, then their interaction with normal photons, that kinetic mixing, must be even weaker than previously thought.
So they put a tighter limit on how strongly these things can possibly interact.
Exactly. They established the strongest limits, the best constraints yet for dark photons in that mass range. They basically drew a new line on the map saying dark photons probably aren't hiding here with this interaction strength. The upper bounds on that mixing parameter are now down around 1013 to 1014 in that range. Okay, so they didn't find the treasure, but they crossed a big area off the map. That is progress. How do these new limits stack up against other searches?
They're pretty significant. These Parker limits are actually stronger than constraints we get from looking at the cosmic microwave background radiation,
Yeah.
the leftover heat from the Big Bang.
Wow, better than looking at the dawn of time.
For this specific mass range, yes. And they also push beyond what laboratory experiments called haloscopes have been able to probe for these very low masses.
Telescopes, what are those?
Those are experiments designed to detect dark matter, often looking for axions, but sometimes dark photons too, usually by trying to coax them into converting into detectable photons inside a strong magnetic field in a resonant cavity.
Okay, so Parker's trip to the sun beat the limits from the CMB and lab experiments for these particular dark photons.
Is this mass window? Yes. It really shows the power of using these, unconventional platforms.
It's like this cosmic game of hide and seek, and we're slowly, systematically ruling out the hiding spots. So what's next? Is the search for dark photons winding down?
Oh, absolutely not. If anything, it's heating up. There's still a huge amount of parameter space left to explore different masses, different interaction strengths.
So Parker ruled out one specific region, but there's plenty more.
Loads more. This work tells us that if ultralight dark photons exist in the range Parker was most sensitive to, they must be incredibly weakly interacting. Or their masses might lie elsewhere, perhaps even lower, below, say, 1015 eVCO.
Even tinier masses.
Yeah.
Wow. How could we possibly look for something that light?
Yeah, that requires different techniques again. This is where another really cool idea comes in. Dark matter radios.
Dark matter radios, like tuning into the dark sector.
Kind of. They're essentially incredibly sensitive electronic circuits, usually LC circuits, cooled down to cryogenic temperatures to minimize noise.
Okay, super cold, super sensitive radios.
And the idea is you can tune this circuit, like an old AM radio, to resonate at the specific frequency corresponding to the dark photon's mass you're looking for.
Resonance again.
Exactly. If a dark photon with that matching mass passes through, its incredibly faint oscillating electric field could, theoretically, induce a tiny, tiny signal in the circuit that you could then amplify and detect.
That sounds incredibly challenging, but also really exciting. Are people actually building these?
Oh, yes. Several experiments based on this concept are being developed and coming online. It's a very active area of research.
The ingenuity is just amazing. Okay, let's try and wrap this up. So, the Parker Solar Probe, built to study the sun, got cleverly repurposed as a dark matter detector.
Right. Using the sun's corona as a natural laboratory for potential dark photon conversion.
And while it didn't find a definitive signal,
Its null result provided the strongest constraints yet on ultralight dark photons in a specific mass and interaction range, pushing our understanding forward.
it really highlights how we can use existing tools and even natural environments in completely unexpected ways to probe these fundamental questions about the universe.
Precisely. The hunt for dark matter is far from over, but each step, even a null result like this, refines the search and gets us closer.
It really makes you wonder, doesn't it? What other unexpected places or methods might hold the key? Could the answer be hiding in, I don't know, deep ocean trenches or signals from merging black holes? It's fascinating to think about.
It really is. And, for you listening, especially if you're preparing for exams like the UPSC,
Yes, good point.
this whole story is a perfect example of the scientific method in action. It shows cutting-edge research, innovative thinking, how scientists deal with null results, and how different fields, astrophysics, particle physics, plasma physics come together. Understanding this process is really valuable.
Absolutely. It's about the fundamental nature of the universe, but also about how we learn about it. Crucial stuff for current events in science and tech. Definitely relevant for prelims and mains.
Couldn't agree more.
So if this deep dive into dark photons and the sun probe sparked your curiosity, please do hit like, subscribe, and maybe drop a comment with your thoughts or questions. We'd love to hear from you.
And if you want to dig into the details of the Parker Solar Probe research itself, the source we discussed today was physics.com.
Great. Well, that's all for this deep dive. Until next time, keep exploring.